Jeez, wow. Sorry about that.
That was the Lord.
All right, so first thing is an announcement. I should let you know that we'll have our third quiz this Wednesday. It will cover the basic chemistry lecture that I gave last week, as well as some additional chemistry that I'm going to cover today. All right, so just to review from last time, we spent a lot of time talking about the structure of the atom, the arrangement of protons and neutrons in the nucleus and the electrons that orbit them, as well as the arrangement of electrons in different shells surrounding the nucleus, and talked a lot about how that influences some of the chemical behavior of the different elements. So one thing that we talked about after going through a lot of that discussion about the atom, we talked about the concept of valence. The word valence means the number of bonds formed by each element. Now, for those of you who've had a bunch of chemistry before, you may confuse the word valence with the phrase valence electrons. Valence electrons refers to the number of electrons in the outermost shell. And it's the number of electrons in the outer shell that determine the number of bonds formed by each element. But the word valence by itself simply means the number of bonds that each element forms. So the valence of hydrogen is 1, only forms 1 bond. Oxygen is 2, nitrogen is 3, and carbon is 4. We also talked about how the arrangement of electrons around the atom influences the bond angles, the angles between bonds. And we talked about the fact that you need really a total of 3 atoms to have 2 different bonds between those 3 atoms to create an angle between the different bonds. And we talked about the fact that those bond angles are controlled primarily by the configuration of electrons around the central atom, the atom at the corner of the bond or the vertex of the bond. And it depends a lot on what are called bonding pairs and lone pairs of electrons. Bonding pairs are the pairs of electrons that actually create the covalent bonds in the first place. And then the lone pairs are pairs of electrons that are not participating in a bond. They're all by themselves. If there are no lone pairs on the central atom at the corner, the vertex of the bond angles, then you end up with different configurations like linear, planar, or tetrahedral. If there's 1 lone pair of electrons on that central atom, then you end up with a pyramidal configuration. And if there are 2 lone pairs of electrons on the central atom, you end up with what's called a bent configuration. And here's a little slide summarizing those. So at the top, you have 3 different configurations where there are no lone pairs on the central atom. The things labeled Y, which are bonded to that central atom, they're trying to get as far apart from one another as they possibly can, because the bonding pairs of electrons are repelling one another. So in a linear arrangement, you end up with something a straight line where the 2 other atoms bonded to the central atom form an angle of 180 degrees. In a planar configuration, you have 3 atoms bonded to a central atom. They try to get as far away from one another as they possibly can, which gives you equal angles of 120 degrees. But then with a tetrahedral arrangement, you have 4 atoms bonded to a central atom. And in order for those atoms to get as far apart as they possibly can, in order for the 4 things labeled Y to be as far apart as they possibly can, they have to spread apart in 3-dimensional space, which results in these bond angles of 109.5 degrees, pointing in 4 different directions. And then at the bottom, we have the 2 geometries where there are lone pairs on the central atom. In the first case, you have a single central pair on that X atom in the middle. That behaves almost as if it's another thing attached to the letter X. So it looks very similar to the tetrahedron, just with the top Y chopped off. The other 3 atoms labeled Y form almost like the legs of a tripod. They're a little closer together. They're not 109.5 degrees apart. They're 107.3, so a little bit less of an angle. And that's because that lone pair of electrons on the central atom is exerting a more powerful repulsive force. It's pushing those bonding pairs apart even more strongly, so the bonding pairs end up being a little closer together. And then finally, you have the bent configuration where there are two lone pairs of electrons on the central atom. So you only have two actual atoms bonded to the central atom. So two letters Y bonded to a single X in the middle. And then the two lone pairs act again almost as if they are other things attached to the central X atom. The two Y atoms end up at an angle of 104.5 degrees, which is even smaller than 107.3. That's because the two lone pairs are pushing even harder against the bonding pairs and pushing the bonding pairs a little bit closer together. So that's all review from last time. New stuff that I want to introduce today is I want to talk very briefly about organic molecules. And I mean, you know, anybody who was a bio major in here, any of the grads who majored in biology would have taken a whole course and possibly multiple courses just in organic chemistry. And, you know, I took organic chemistry when I was an undergrad, and I find that having some knowledge of that is still helpful to this day. But what I'm going to talk about today is, I think, most of what medical illustrators would need to know about organic chemistry. You don't necessarily need a whole course in organic chemistry to be a medical illustrator, but it's still very helpful to have some basic understanding of organic molecules, because organic molecules and organic chemistry is the whole basis for biochemistry. It's the whole basis for the molecules of life that we'll be talking about for the rest of the semester. So I want to talk a little bit about the naming of organic molecules. I don't expect anyone in this class to be an expert at naming organic molecules, but I want you to have some familiarity with where organic compounds get their names from, because you're going to run across these names constantly in this field. And it's helpful to have some idea what these names are referring to, and it's helpful to have at least some basic idea of the naming system that goes into producing these sometimes very complicated names for biological compounds. So most organic compounds have a common name, like the word glucose or something like that. But then every organic compound also has an official chemical name known as an IUPAC name. And IUPAC is short for the International Union of Pure and Applied Chemistry. And this is an organization that has created a whole bunch of rules about how to name biological molecules or organic molecules. And actually, really, it would apply to non-biological molecules too. Really, any molecule would have an IUPAC name, but we're focusing just on the organic molecules here in this class. That IUPAC name is derived from the three-dimensional structure, actually not even really the three-dimensional structure, just the general structure of the molecule. If you look at any molecule, if you follow a set of IUPAC rules, you can actually come up with the name for that molecule, the IUPAC name, because that name is based on the molecule structure. And conversely, if you have the IUPAC name, you can determine the structure of the molecule just from the name. There's enough information embedded in the name that you should actually be able to draw the structure. I'm not going to, as I said before, I'm not going to expect you to be experts in IUPAC naming system. I want you to just know some of the basic rules that are applied to the naming of organic molecules. In addition to the common name, like the word glucose, and the official IUPAC name for that compound, a lot of consumer products also have a brand name. So an example of that would be something like Tylenol. You know, you go to the drugstore, you go to Wegmans, whatever, and you got a headache, you want to get some Tylenol. So Tylenol is a brand name. It's you know, it's a registered trademark of whatever, I forget what company makes Tylenol, but so that's their brand name. The generic name for Tylenol is acetaminophen. That's the active compound in Tylenol that makes it a pain reliever. But then acetaminophen has an IUPAC name. So acetaminophen is the common name. The IUPAC name for acetaminophen is N-acetyl para-aminophenol. And if I were to dissect that name and think about what all the parts of that name mean, I could probably draw that. I don't consider myself a world's expert on IUPAC naming either. But there's enough information in there. This one's actually simple enough, believe it or not, that I could probably draw that. Because I know what phenol means. Anytime you see that PHEN, phen prefix, that's referring to a benzene ring. That's a 6-carbon ring with a bunch of double bonds in it. And the OL at the end tells me that it's an alcohol. So phenol is a 6-carbon ring with a bunch of double bonds in it with a single OH group attached to it, which is what makes it an alcohol. And aminophenol tells me that there's also an amino group attached to that benzene ring. And the word para tells me that the amino group and the alcohol group are on opposite sides of the 6-carbon ring. There's a bunch of words like para and meta that tell you the arrangement of things attached to the 6 carbons on a benzene ring. And then the acetyl tells me that there's also an acetic acid group that has bound to, in this case, to the amino group in this ring. So, you can draw this thing just based on that name. Another example, just happened to pick over-the-counter medicines. Mucinex is an example of something called an expectorant that loosens up chest congestion. And the generic name for Mucinex is guaifenesin. So you can now buy a generic guaifenesin. You don't have to buy the Mucinex brand name. And the IUPAC name for guaifenesin is this 3,2-methoxyphenoxypropane 1,2-diol, which is a mouthful. And I wouldn't expect you to be able to draw this one. I wouldn't expect you to be able to draw either of these. Even after the end of today's lecture, we're not going to go into the IUPAC naming quite to that extent. But I could probably draw this because I know how to dissect the name. The key thing here is actually the word propane. That's actually the main sort of chain of carbons in the molecule. Propane is a 3-carbon chain, which we will talk about shortly. The 1,2-diol tells me that there are alcohol groups on the number 1 carbon and the number 2 carbon of that propane carbon chain. So there's an OH group on the first carbon and an OH group on the second carbon in that propane. And then on the 3rd carbon of the propane, you have the rest of that stuff. So the 3 tells me that 2-methoxyphenoxy is on the 3rd carbon of the propane. And once again, you can dissect that part of the name. Phenoxy, there's that PHEN again, that prefix phen, which is telling us that once again, there's a benzene ring in here attached to an oxygen. And then the methoxy means there's another oxygen and a methyl group, which is CH3 attached to that. So you could probably draw this too from the IUPAC name. So let me walk you through a few of the IUPAC rules so that you can at least begin to see how these names are constructed and learn how to name at least some basic organic compounds. So for organic molecules, typically the first thing you do when naming the molecule is you look to see if there's a chain of carbons in the molecule, a continuous chain of carbons that are covalently bonded to one another. And you count the number of carbons that are connected to one another in that chain. Then you take a look at that chain and you look at the kinds of bonds that exist between those carbons in that continuous carbon chain. Are they all single bonds? Is there a double bond? Are there multiple double bonds? Is there maybe even a triple bond between the carbons in that continuous chain? Then you'd look to see if there are any side branches branching off of that carbon chain. And then finally, you'd look for special side groups that might be attached to that carbon chain. So I already mentioned alcohols before, which means just adding OH to the side of a carbon chain. You could have something called a carboxylic acid, which is a double bonded oxygen and an OH attached to one of the carbons to create what's called a carboxylic acid. You could have ketones and aldehydes, which are just double bonded oxygens attached to one of the carbons, either in the center of the chain or at the end of the chain. You can have amines and amides, which are nitrogen containing side chains. And you can have these phenyl rings. There's that PHEN again, which means a benzene ring, a 6-carbon ring attached to the larger molecule. And there are other things too, but this covers, you know, a very large number, the majority of the organic molecules that you'll encounter when looking at, you know, at biochemistry or molecular biology. So I mentioned that part of the name of the molecule is based on the number of carbons in a continuous chain. So you would, first thing you do when you look at a molecule is you would try to identify the longest continuous chain of carbons in the molecule. And I'll come back and mention this probably 3 or 4 times, but when we draw the molecules, we don't necessarily draw the longest chain, you know, directly from left to right. Sometimes it starts at the top and then comes down and then makes a turn and makes a bend and heads to the bottom and then turns left again. The carbon can actually make lots of bends, or excuse me, the carbon chain can make lots of bends and turns, but as long as all the carbons are bonded to one another, it represents a single continuous chain. So you identify that continuous chain of carbons and count how many carbons are in that continuous chain. And that becomes the basis for the main part of that molecule. And the beginning of the name of the molecule will start with a prefix depending on the number of carbons. So if you have just a single carbon atom, there may be other things attached to it, but as long as it's just one carbon all by itself, maybe some hydrogens, maybe an OH group, you know, maybe some other stuff attached to it, we would call that something meth something. The end, we'll talk about the suffix or the ending of the word in just a minute, but this would be the prefix or the beginning of the name. We did talk about something last week that starts with meth, something called methane, which is just a single carbon surrounded by 4 hydrogens. It's the classic example of the carbon tetrahedron. So that's one example of something that starts with that prefix meth. There's another name that's occasionally used in place of meth. Sometimes you see form as a prefix. So things like formaldehyde or formic acid, they use the form instead of the meth for a 1-carbon chain. If there are 2 carbons bonded to one another, then we use the prefix eth, or occasionally instead you see acete, as in like acetic acid, which is vinegar. 3-carbon chain would be prop, 4 is but, 5 is pent. The first 4 are harder to identify. If you know any Latin, the last 6 of them are easy, because 5, you know, pent, like a pentagon, 6 hex, hexagon, 7 is hept, 8 is oct, 9 is non, and 10 is dec. Then after you've identified how many carbons are in the chain and you've got the prefix for your IUPAC name, the ending of the name tells you what kinds of bonds are present between those carbons. If all of the carbons in the chain are bonded to one another by single bonds, we call that kind of molecule an alkane, and the name of the molecule ends in the letters ANE. So examples of that would be things like methane or propane. Propane is a chain of 3 carbons that are all bonded to one another by single bonds. If there's a single double bond, whoa, interesting echo. If there's a single double bond somewhere in the carbon chain, you know, connecting 2 of the carbons to one another, we call that kind of molecule an alkene, and the name of the molecule would end in the letters ENE. So propene is a 4-carbon chain, and 2 of those carbons are connected to one another by a single double bond. Hexene would be a 6-carbon chain with 1 double bond connecting 2 of the carbons in there somewhere. And frequently these things will also have a number in front of them that tells you where that double bond is located in the chain. If there are 2 double bonds present somewhere in the chain, we call that kind of molecule an alkadiene, and the name of the molecule ends in diene. So pentadiene Penta tells me that there are 5 carbons in the chain. Diene is telling me that there are a total of 2 double bonds somewhere in that 5 carbon chain. You can have 3 double bonds. We call that an alketriene, and they end in triene. So octatriene would be an 8 carbon chain with 3 double bonds scattered, somewhere along the chain. And then finally, if you have a triple bond between 2 carbons, we call that kind of molecule an alkyne, and the molecule would end in YNE. So ethine would be a 2 carbon chain where the 2 carbons are bonded to one another by a triple bond. Remember that acete is sometimes a substitute for eth, so this is also known as acetylene, which is the gas they use for cutting torches, for cutting metal. So here's some examples of alkanes. So we've got methane. Now in methane, you've only got 1 carbon, so the carbon's not really bonded to any other carbons, but it's single bonded to all of the hydrogens around it. Propane, 3 carbon chain with single bonds. Butane, 4 carbon chain with single bonds. Octane, 8 carbons, all bonded to one another with single bonds. Now notice that in these molecules, they're also surrounded by hydrogens. And we have enough hydrogens to satisfy the valence of each carbon. So in methane, carbon always forms 4 bonds. The valence of carbon is 4. So the carbon happens to be bonded to 4 hydrogens. If you look at the propane molecule, the carbon on the far left is attached to 1 other carbon in the middle, but that means the carbon on the left is only bonded to 1 other carbon, so it has 3 additional bonds, and we just fill those all in with hydrogens. Same with the carbon on the right. The carbon on the right is only attached to 1 other carbon, so it also has to have 3 hydrogen attached to it. The carbon in the middle, though, is attached to 2 other carbons, so 2 of its bonds are used to form the carbon chain, but that means it still has 2 other bonds that have to be filled in with hydrogens. And that would be the same with any of these other molecules as well. The carbons on the ends would be attached to 3 hydrogens. The carbons in the middle of the chain would be attached to 2 other hydrogens. These are what are also known as saturated compounds, which simply means they are saturated with hydrogens. They have every possible hydrogen that they could have. Because the carbons are only single bonded to one another, all of the remaining bonds are attaching to hydrogen atoms. This concept of saturated carbon compounds will come up again later in the course when we talk about fats, lipids, because we talk about fatty acids or lipids as either being saturated or unsaturated, which has a lot of implications for your health. Because generally speaking, unsaturated fats are healthier, or at least that was the typical thinking. I'm not sure what the current consensus on that, but generally, unsaturated fats, which come from vegetable sources, are usually considered healthier than saturated fats that come from animal sources like steak or butter. Okay, so here are some examples of alkenes, alkadienes, alketrienes, and alkynes. So the first example is an alkene. It's called 2-pentene. So the pent tells me that there are 5 carbons in the chain. And the fact that it ends in ENE means it's an alkene. That tells me there's 1 double bond located somewhere along that 5 carbon chain. The 2 at the beginning tells me that the double bond lands after the 2nd carbon. Now, before I move on, imagine that this molecule is floating around in 3-dimensional space. They're not always going to have, the number 1 carbon over here on the left and the number 2 carbon next to that and the number 5 carbon at the far right. I mean, just imagine that this thing spun around in 3 dimensions. We number the carbons in the chain starting at the end that's closest to the first unique thing. Meaning if there was a side chain like an OH or another small carbon chain attached to the main chain, we would start numbering the carbons closest to that side branch. Or in this case, the double bond is closer to the left end than it is to the right end. So we actually start numbering the carbons from the left side, not from the right. Now, even if I flip this around and had the mirror image and the double bond was farther over to the right, it would be closer to the right end than to the left. But so we start numbering the carbons closest to where that double bond is. So that means that the left-hand carbon here is the number 1. The next carbon is number 2, then 3, then 4, then 5. The 2 tells me that the double bond sits right after the second carbon in the chain. This next molecule is another example of an alkene. This is hexene. The hex telling me that there are 6 carbons. The ENE telling me that there's a single double bond in here somewhere. The 1 tells me that the double bond comes right after the number 1 carbon. Now, this is an example of the fact that we don't automatically start numbering the carbons at the left, because you have to realize that this thing's floating around in 3 dimensions. You could just as easily flip it around. We start numbering closest to the first unique thing, in this case, the double bond. Or if there, like I said, if there was something branching off of that carbon, some side group or something, we always start numbering closest, and we number the carbons starting at the end closest to the first branch point or the first double bond. The next one is a alkadiene, so something that has 2 double bonds somewhere along the chain. It's 1,3-hexadiene is the name. So hex is telling me that it's a 6 carbon chain. Diene is telling me that there are 2 double bonds somewhere in the chain. And the 1 and 3 tell me that the double bonds are located right after the first carbon and the third carbon in the chain. So again, because the first double bond is closer to the right in this case, we start numbering the carbons here at the right. So that'd be the number 1 carbon, double bond comes right after that, number 2, and then number 3 carbon, the double bond, the other double bond comes after the number 3 carbon. So we'd call this 1,3-hexadiene. We don't start counting from the other end. This would not be 3,5-hexadiene. We don't start counting at the left here. We start counting closest to wherever that first unique thing is, in this case, the double bond. Here's an alkatriene, an example of a molecule with 3 double bonds in it. It's hept. So hept tells me that there are 7 carbons in the chain. Triene tells me there are 3 double bonds. Once again, we start numbering closest to wherever that first unique thing is. So there's a double bond right after the first carbon here on the right. If we look on the left, there is no double bond after that first carbon on the left. So that means we start numbering the carbons from the right-hand side. So there's a double bond after the number 1 carbon, the number 2 carbon, and after the number 5 carbon. So 1, 2, 5 heptatriene. And then finally at the bottom is an alkyne, something that has a triple bond in it. And this is the example I gave you before of ethine or acetylene. Eth telling me that there are 2 carbons in the chain and they happen to be bonded to one another by a triple bond, meaning there's only 1 bond left over at each end for 2 additional hydrogens. These are all examples of what are called unsaturated compounds, and you might have to stand up to see that on the computer screen because it's cut off at the bottom of the slide. The pentene and hexene that have just a single double bond, they are unsaturated compounds, meaning that since some of the bonds are involved in attaching carbons to one another, there are 2 missing hydrogens in a sense. It's not fully saturated with hydrogens. It doesn't have every possible hydrogen in there. Same thing with the hexene. And in the case of hexadiene, heptatriene, and acetylene, these are known as polyunsaturated compounds because they're missing multiple hydrogens, not just 2. They're missing, 4 or 6 hydrogens because of the presence of multiple bonds. And again, this has implications for your health that when we talk about fats later in the semester, we'll talk about the fact that the fatty acid chains, the make up a good portion of each lipid molecule or each fat molecule. If they are unsaturated, they have a little different structure than if they're saturated. And the thinking, at least last I checked, was that the unsaturated ones are healthier for you. Right. So in addition to the main carbon chain, you may also have shorter side chains attached to the larger chain. So let's say you had like an 8-carbon chain, you had octane. You might have like a little side branch with 2 carbons off to the side of the main octane molecule. Anytime you have a chain of carbons that's a side branch off of a bigger chain, we call that side group an alkyl group. And the prefix for the name of this side group uses the same numbering. So meth for 1 carbon, prop for 3, but for 4, oct for 8. But then we add the ending YL to make it an alkyl group. So a 1 carbon side chain would be a methyl group, a 3 carbon side chain would be a propyl group, a 4 carbon side chain would be a butyl group, and so on. So here you see those. Again, it uses the number of carbons. We use the same prefixes. If that molecule was an alkane, we'd call it methane or ethane or propane and so on. But if that molecule is a side chain, a branch off of a larger molecule, then we would call it either like a methyl group. Notice that this is just CH3, and there's 1 bond that's attaching it to whatever the bigger molecule is. A 2 carbon side branch or side chain would be an ethyl group. 3 carbon side chain would be a propyl group, butyl, pentyl, hexyl, heptyl, etc. So when you have a carbon chain that has a side branch off of it, the way we name these things is we start out by figuring out the name of the longest continuous chain of carbons in the molecule. So we would look and examine the molecule, and in this case, we've got 1, 2, 3, 4 carbons. So the longest chain of carbons in this molecule seems to be 4. Now here's an important point. The way I've illustrated this, I've drawn this CH3 group, which would be a methyl group. I've drawn it in blue, indicating that that's a side chain. But I could have just as easily started my longest chain by counting from that carbon, the one in blue, call that the number 1, and then 2, 3, and 4. It actually would have been exactly the same molecule. Don't assume that you always have to start counting from the left end of the molecule. You might start counting at the right end. You might start counting at the top and work your way down, or even the bottom and work your way up. But in both cases, if I start counting with the red one that's numbered 1, that means I have a methyl group attached to the number 2 carbon, shown in blue. But if I had instead identified that blue carbon as number 1, then the red one that's currently numbered number 1 would also be, it would be a methyl group attached to the number 2 carbon in the chain. So these would be identical molecules regardless of whether I started with the red carbon or the blue carbon. So once I figured out what my longest continuous chain of carbons is, in this case it's 4 no matter which way I start counting. So I know that the basic molecule itself is called butane, because but is the prefix for a chain of carbons with 4 carbons in it. So I identify it as butane. I number the carbons starting closest to that first branching point. So since I'm going to call that blue carbon, I'm going to call that a methyl group. That means that my first branch point is closer to this number 2 carbon. So I start numbering the carbons 1, 2, 3, 4. I wouldn't start at the other end because then I'd have 1, 2, 3. I'd have my methyl group on the third carbon instead of the second one. So I start numbering my carbons closest to the first branch point. After I've identified the main chain and named it and numbered the carbons, then I figure out what my alkyl groups are that are attached to that main chain. So in this case, I've got a 1 carbon chain, which would be a methyl group, attached to the number 2 carbon of the butane molecule. So that's called methyl butane. We put the name of the side branch first and the name of the main molecule at the end, which is a little weird with IUPAC naming. With IUPAC names, you almost always want to look at the end of the name first, because that's going to tell you your main chain. And then everything else that comes before that are usually side branches off of that. So 2-methylbutane says I've got a molecule of butane with a methyl group attached to the number 2 carbon of the butane. So here I make the point that all of these bonds between these carbons are movable. They can all rotate around, which means that drawing the molecule that I've drawn here on the left, it's actually identical to this other molecule that I've drawn on the right, because there's been rotation of that number 3 carbon. So initially I drew the molecule with the main carbon chain simply numbered from left to right, but that's actually exactly the same molecule as the one I've drawn over here on the right, where I started numbering the chain down at the bottom and then came up and then made a right turn to continue. The key is you have to find the longest continuous chain of carbons, and don't be fooled by the fact that the chain may actually bend or zigzag around. So in this first drawing, this first way of illustrating the molecule, it's very simple and straightforward. You know, we can count our continuous chain of carbons, 1, 2, 3, 4, 5, 6, 7, 8. So I know that the molecule is called octane because it has 8 carbons, and the carbons are all bonded with single bonds. So it's octane, A-N-E. There are no double bonds in there, so we don't use E-N-E. And then there's a methyl group, a 1 carbon side chain. In this case, it's attached to the number 3 carbon of the octane. I'm not going to number my octane starting at the far right, because then I wouldn't get to that methyl group until 1, 2, 3, 4, 5, 6. I always start numbering the carbons in my long chain closest to wherever that first branching point is. So what I have here is a molecule of octane with a methyl group attached to the number 3 carbon. So the name is 3-methyl-octane. But it's exactly the same, even if I had drawn it a different way. In this case, I still want to look for that longest continuous chain of carbons. I don't automatically just start here at the left and count. If I look down here, I realize, oh, I've got 1, 2, 3, 4, 5, 6, 7, 8 carbons that are all connected to one another. So I would start numbering down here at the bottom carbon, because that's closest to this first branch point. It's still octane, and it still has a methyl group at the number 3 position. So it's still 3-methyl-octane. It's the exact same molecule, just drawn 2 different ways. Now we get into one that's a little more complicated, because now we have multiple alkyl groups, multiple side chains branching off of the main chain. So the first thing we have to do, if I just showed you something like this picture on the left, first you've got to figure out what is our longest continuous chain of carbons. So first let me see if I can get my little annotation tools. I hate these things because they don't work very well, but they might work for this purpose. Okay, that's how it goes. All right, so let's see if this works. If I look at my carbon chain, there's a temptation to start here at the far left and count. So if I started there, I'd have 1, 2, 3, 4, 5, 6, 7. But that may not be the longest continuous chain. What if I start up here at the top? I go 1, 2, 3, 4, 5, 6. Okay, well, that's even shorter. What if I went a different way and went 1, 2, I'm doing this with the mouse because the Wacom's not working for some reason, 3, 4, 5, 6, 7. All right, well, there are two different ways I could count this thing and end up with 7, but still not quite right. Because if I start down here, I can go 1, 2, 3, 4, 5, 6, 7, 8. Right now I've got a continuous chain of 8 carbons. That's my longest chain. Now, do I start counting down here? 1, 2, 3? Or would I start over here? 1, 2, 3. I'm going to start over on this end because that's going to be closest to the first branching point. So this is my 1 carbon, 2, 3. All right, I'm going to give up because I can't do this with a mouse. But you can see that I've numbered them over here on the right. So I've got my number 1 carbon, 2, 3, 4, 5, 6, 7, 8. And I started counting down here because it's closest to the first branching point. There's a side branch on the number 3 carbon. If I had started counting on the far right, I wouldn't hit my first side branch until I got to the 4th carbon. If I had started from here, 1, 2, 3, that doesn't look like a 3, 3, 4. So that's why I started counting from the bottom, because it's closest to my first side branch. So then, once I've numbered my main molecule, I know that it's octane. I've got a continuous chain of 8 carbons, all attached by single bonds, so it's octane. That makes this side branch a methyl group. So it's a 1 carbon side chain attached to the number 3 carbon of the octane molecule. So that's 3 methyl. This side chain, this is an ethyl group because it's a 2 carbon chain and it's attached to the number 5 carbon. So it's 5 ethyl. Now here's something that I find a little weird about the IUPAC naming system. I don't quite understand why they have this rule, but it's a rule. If you have a bunch of side chains, you list them in alphabetical order, not numerical order. My temptation would be to say, let's start naming the side groups according to which carbon they're on the main chain. So I'd be inclined to call this 3-methyl, 5-ethyl octane. But no, that's not the way it works. You list the side chains in alphabetical order. So because ethyl becomes before methyl in the alphabet, it's actually 5-ethyl, 3-methyl octane is the full name of that molecule. All right, let's see. All right, here's another one. This one's got 3 side chains. So same exercise. Try to figure out what's the longest continuous chain of carbons. Now, it just so happens that in this one, it does start here at the far left. Whoops, that's not what I wanted to do. It does happen to start over here. It keeps, all right. All right, now my annotation tools refuse to work, so we'll just not use them. You'd have to explore a bunch of different ways of counting the carbons. One thing I will tell you is that I could start at the far left, the one that I've numbered number 1 carbon over here in red on the right-hand side. But I could have just as easily started with this blue carbon that I've identified as the methyl group. If I had started down here and called this blue one the number 1 carbon, then the one that's numbered 1 in red would have been a methyl group attached to the number 2 carbon of the main chain. It would have been the same thing, regardless of where I started counting in this case. So when I go through the exercise of figuring out what my longest continuous chain is, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that means the main molecule is decane. And I start numbering the 10 carbons closest to the first branch point. So that means there's a number 1 carbon here, number 2 carbon has a methyl group on it. Number 4 carbon has a methyl group on it. Number 7 carbon has an ethyl group on it. So I've got 2 methyl and 4 methyl and 7 ethyl. Once again, IUPAC says put them in alphabetical order. So it's 7 ethyl. But now I've got 2 methyl groups. I could say 7 ethyl, 2 methyl, 4 methyl decane, but that's kind of dumb. It's redundant. So we put the 2 methyl groups together. We call them 2,4-dimethyl. So 7 ethyl, 2,4-dimethyl decane. So that tells me I got an ethyl group on the number 7 carbon and 2 methyl groups, 1 on the number 2 carbon, not 1 on the number 4 carbon. All right, so that's a lot of naming of, IUPAC names for organic molecules. We'll come back to that a little bit more in a few minutes, but let me also talk a little bit about the 3D geometry of some of these carbon chains. So these pictures that I keep sharing with you, showing you these perfectly straight carbon chains all linked together with single bonds and a whole bunch of hydrogens single bonded. These are known as Kekule diagrams, named after an Austrian chemist back in the 1800s, who was one of the first people to use this kind of depiction for molecules. Turns out he actually wasn't the first. There was an English scientist who did this before him, but Kekule always gets credit for it. But at that time, we didn't know very much about the 3-dimensional arrangement of atoms in molecules. In fact, we knew very little at that time. So they knew which atom was bonded to which other atom, but they really didn't know anything about what the atoms looked like in 3 dimensions, or what the molecules looked like in 3 dimensions. So these simplified Kekule drawings are not geometrically accurate. They're not meant to be. In reality, you have to imagine that every single one of these carbons is sitting at the center of a tetrahedron. So here's our tetrahedral model of the carbon atom. We've got the carbon sitting at the center, attached to 4 other bonds. And imagine the 2 bonds at the top are lying in the same flat plane. They'd be like right in the plane of the screen, of the projector screen. But then another bond, the one that gets a little fatter, that has a little sense of perspective to it, that one would be coming towards us out of the screen. And that other one with the little skinny line would be going away from us into the screen. So we'd have these 4 bonds all arranged in 3 dimensions in space, all separated from one another by these equal 109.5 degree angles, and forming this tetrahedral arrangement. Now then, when you take that 1 carbon and you attach it to another carbon, you have to imagine that each carbon in that chain is also in this tetrahedral arrangement. So all these bonds are arranged in kind of this tetrahedral shape relative to one another. When you start stringing these things together into longer chains, you get this kind of zigzag effect where the carbons kind of zigzag back and forth. And then you've got all the hydrogens kind of sprouting out, either some of them coming towards us and some of them going away from us in three-dimensional space. And because a straight chain of carbons is really this kind of zigzag, where the carbons are zigzagging back and forth at angles of 109.5 degrees, sometimes we can draw a long chain of carbons as just this zigzagging line. You see that zigzagging line in a picture of a molecule, it's representing a quote unquote straight chain of carbons, but it's not truly straight because each carbon kind of zigzags back and forth with these 109.5 degree angles. As soon as you introduce a double bond to the molecule, that changes the geometry and it changes that zigzag a little bit. So we didn't really talk about the geometry of double bonds before. When I went through that whole thing about, linear and planar and tetrahedrons and pyramids and bent molecules, all of that stuff, we were just limiting ourselves to talking about single bonds. As soon as you throw a double bond in there, the bonds on that carbon now start to look a little bit like our planar molecule. Remember, in the planar molecule, we had an atom in the center with three identical atoms surrounding it. And those identical atoms were all separated from one another by equal angles of 120 degrees. When you have a double bond between two carbons and then a couple hydrogens attached to it, it's almost like the planar molecule, but the bond angles are not quite the same. The angle between the single bonds is a little bit less than 120. It's down to 116.6 degrees. The angle between the single bond and the double bond is a little bigger than 120, 121.7. Same thing down here. This is another angle between a single bond and a double bond. And the reason for that is because the double bond consists of two bonding pairs of electrons. They push harder than one bonding pair of electrons. So a double bond, in a sense, pushes harder than the single bonds. So there's a bigger angle between the double and single bonds than there is between two single bonds and between one single bond and another single bond. And if you look at how this impacts the structure of our three-dimensional chain of carbons, there are two different configurations for these double bonds. There's what's known as the trans and the cis configurations. Trans meaning opposite sides and cis meaning same side. And it's referring to whether these hydrogens here are on opposite sides or, as you see here in the cis molecule, whether they're on the same side or not. Either of these puts a little bit of a kink in the chain. The cis configuration actually puts a little bit more of a kink in the chain, a little bit more of a bend, but they both do cause the chain to deviate a little bit from that sort of perfectly straight zigzagging pattern that we saw previously, where you have always these uniform 109.5 degree angles. You may not realize it, but you've actually seen this illustrated probably very frequently in your biology textbooks. If you recall seeing the classic lollipop representation of the lipid bilayer, there's a reason why the lipid tails look like little zigzags, because the lipid tails, they're actually what we call fatty acid chains, are chains of carbons that have that back and forth zigzagging pattern to them. Over here on the left is an illustration I did years ago showing what the actual structure of these lipids look like in the cell membrane. And I did a little color coding here. There's a little blue in the background behind one end of the molecule. That represents the hydrophilic region, or what's known as the polar region. That's what's always represented as the blue head on the lollipop. That's the part that's attracted to water. So it's either attracted to the extracellular fluid outside the cell or attracted to the cytoplasm inside the cell. And then the yellow background corresponds to the yellow zigzagging fatty acid tails. And it's a little harder to tell in this representation of the molecule. You don't necessarily see the zigzag effect, but imagine that we've got little, carbon atoms that are kind of zigzagging back and forth at 109.5 degree angles. The other thing you can see here is the difference between saturated fatty acids. So this molecule on the right, it's a glycolipid. It's a combination of a sugar molecule and some fatty acid tails, but the fatty acid tails, even though they have that zigzagging, you can see that they're still basically straight because they're fully saturated. There are no double bonds in here. Then on the left, we have an example of a phospholipid, which has a phosphate group and then has fatty acid tails. And you can see that one of the fatty acid tails here has a prominent kink in it, prominent bend. That's because of the presence of a double bond in there. So this is known as an unsaturated fatty acid. The representations of the lipid bilayer that you see on the right, we'll talk about this later in this course because we'll talk about representations of things like lipid bilayers. The blue lollipops is the way that I always used to draw lipid bilayers because I knew everybody would recognize immediately what it was. At least anybody who had any biology in their life would know immediately what it was. But I just from an aesthetic point of view, I hate them. I hate the little blue lollipops. I think they look very childish, very cartoonish. So I've tried to get away from the simplified blue lollipops and try to move towards something that's a little closer to reality, like you see here at the bottom. Still got little blue lollipop heads, but they're not quite as vivid. They're not as saturated, so they're toned down a little bit. And then instead of just little yellow lightning bolts for the zigzagging fatty acid tails, I've started to replace them with just these little clusters of gray balls that are not quite so obnoxious, in being vividly colored. And they're a little closer to what's really going on here with that zigzagging of the carbons. And you'll notice that there's a little variety in these. This is actually something that I use as a pattern brush in Illustrator to create a repetition of these lipids. If I ever want to really quickly draw a lipid bilayer. Okay, what time is it? All right, well, this would be a good time to take a short break. So take 10 minutes and then we will resume. Okay, so we've talked about mostly just chains of carbons with a bunch of hydrogens on them, but there are all kinds of other side groups and sort of side chains that dramatically influence the reactivity, the chemistry of these carbon chains. So there's a group of side groups that contain oxygen. So these include the alcohol groups, ethers, aldehydes, ketones, carboxylic acids, esters, all of which are going to have very, very different chemical properties, and all of which are involved in biological molecules. There are also some side groups containing nitrogen, the amines and the amides. And then there are a bunch of carbon rings. There are cyclic alkanes, which would be rings of carbons that are connected by single bonds. Then there are benzene rings that are connected by double bonds. So let me go through some of the side chains that contain oxygen. So you make something an alcohol by adding OH to it. The OH is sometimes referred to as a hydroxyl group, but you could also call it an alcohol group, because if you add OH to an organic molecule, you turn it into an alcohol. So Here's the OH, attached to a carbon chain. And here's one example of that on the right. We've got a 2-carbon chain, so we know the prefix is F. If this was just a 2-carbon chain surrounded by hydrogens, we would call it ethane. But when you add that alcohol group, you drop the E off the end and add OL to the end. So ethane becomes ethanol. This is the kind of alcohol that you can drink. If you had methanol, which would just be a single carbon with an OH, you don't drink that because you will die. So you can only drink one very specific kind of alcohol. And then there's propyl alcohols and butyl alcohols, and again, any carbon chain, you add an OH to it and you turn it into an alcohol. An aldehyde is simply the presence of a double bonded oxygen at the end of a carbon chain. And the naming sounds a little bit like the alcohol, but it's subtly different. Instead of adding OL to the end of the name, you add AL for alcohol. So ethane becomes ethanal with the AL at the end. So it's just this oxygen double bonded to a carbon at the very end of the chain. A carboxylic acid is a molecule that has a double bonded oxygen and a hydroxyl group. So it's almost like a combination of an alcohol and an aldehyde. You're adding both the OH and the double bonded oxygen to one of the carbons at the end of the chain. By the way, the hydrogen on this OH group, in the case of this acid, this carboxylic acid, that H dissociates, meaning it splits off. When you put this stuff in water, the H splits off to become a hydrogen ion, H+, and that makes the solution acidic. So these things are called carboxylic acids because they really are acids. The hydrogen dissociates, becomes H+, and acidity is a measure of the concentration of H+ ions in solution. So these things truly are acids. The naming of these carboxylic acids, you take the name of your carbon chain, drop the E from the end and add oic acid to the end, OIC acid. So once again, just sticking with the same theme of ethane, if you take ethane and turn it into a carboxylic acid, it becomes ethanoic acid. But remember that the prefix acete is sometimes used in place of eth. So this is acetic acid or vinegar. A ketone is similar to an aldehyde in that we're adding a double bonded oxygen. But in the case of an aldehyde, you add the double bonded oxygen to the carbon at the end of the chain. In the case of a ketone, you add that double bonded oxygen somewhere in the middle of the chain. And it may be surprising, but that does influence the chemistry pretty significantly. There's a big difference in chemistry between an ethanol, or excuse me, an aldehyde with the oxygen at the end, and a ketone with the oxygen in the middle. To make these things, to name these things, you just take the prefix, you take like propane, drop the E and add ONE at the end. I couldn't stick with ethane in this case and turn it into a ketone, because if you have a 2-carbon chain and you put a double bonded oxygen on one of those 2 carbons, by definition, it has to be an aldehyde. You have to have at least 3 carbons in order to have one in the middle to turn it into a ketone. So this would be propane, but you add the oxygen in there and it becomes propanone. An ether, you may have heard of ether as anesthesia that's used to put people to sleep in surgery. But the ether that's used in surgery, I don't know how much it's used anymore, but it was first introduced in the 1850s, I believe, and was the anesthesia of choice, for at least a century. That's just one very specific type of ether. Ether is actually a broader category of organic molecules. And an ether represents two alkyl groups, so two short carbon side chains linked together by an oxygen in the middle. So here's an example of an ether. This is known as ethyl methyl ether. It's a methyl group, a single carbon alkyl group, and an ethyl group, a two carbon alkyl group, and they've then been joined by this oxygen. And you know, I would look at this and I'd want to call it methyl ethyl ether, just because the way it's drawn, the methyl group is on the left, but same with IUPAC naming. You know, you list the alkyl groups in alphabetical order, so it's always ethyl methyl instead of methyl ethyl. An ester is a little bit like an ether in the sense that you are joining two alkyl groups together, but instead of just joining them by an oxygen, there's also this double bonded oxygen on one of them. And so here we see an example where we've got an ethyl group on one side, a propane group or propyl group on the other side. It's a 3 carbon chain. And the way you make these names is you take the name of the first alkyl group, the second alkyl group, and then you add O8 at the end. So it's like ethyl propyl, or ethyl propane, but then you make it ethyl propanoate. You add that OATE to the end of the name. The way you make these things actually is you take an alcohol. So in this case, if you started with ethyl alcohol, which would be the 2 carbon chain with an OH on it, and then you have a carboxylic acid. So if you imagine you had propanoic acid, 3 carbon chain with a double bonded oxygen and another OH on the end, you stick those together and a water molecule breaks off. The hydrogen from the alcohol and the hydroxyl group from the carboxylic acid, actually probably the other way around. The OH from the alcohol and then an H from the acid, they would join together to make HOH or H2O. So a water molecule would be released, and then the 2 alkyl groups would then be stuck together by this oxygen here. These are fun molecules, these esters. They're responsible for a lot of the flavors and smells of your favorite foods. So there's one ester for the smell of strawberries and an ester for the smell of apple, and vanilla is an ester. Pineapple, banana, lots of fruity smells and flavors and things are all come from esters. When I took chemistry in high school, we made esters. You could always tell every year when the chemistry students were making the esters, because when you're walking down the hallways, all of a sudden you get this blast of banana smell in your face. It's like, oh, they're making esters in chemistry class. Of course, just a bit of a tangent, but when the stuff is really concentrated, when you're the one who's actually making it in the lab, it smells horrible. Like when these things are really concentrated, they smell awful. It's only when they're in very low concentrations that they actually smell good. So like halfway across the school, it smelled like bananas, but right in the chem lab, it smelled like, I don't know what it smelled like, but it wasn't good. Hey, in addition to all of those different chemical groups that contain oxygen, there are also some important side chains that contain nitrogen. One very common one that you see a lot in a lot of organic molecules is an amine group, which is NH2, that's added to the end of a chain. And to make a name of something that has an amine group, you simply add the word amine to it. So This is an ethyl group, a 2-carbon side chain with an amine at the end, so that's ethylamine. An amide or amide is very similar, but with the presence of a double bonded oxygen on that carbon at the end. So it looks like an amine, but you've got that extra double bonded oxygen there. So in this case, you just add amide or amide to the end. So this is ethylamide or ethanamide. That would mean the same thing. Just an ethyl group with the amide ending at the end. So you have probably heard of these things, amino acids. Amino acids, of course, are the building blocks of proteins. And almost all of the amino acids have this basic structure. There's one exception that doesn't look exactly like this, but most of the amino acids have this basic structure. You've got a central carbon that's referred to as the alpha carbon. And then on one side, you have an amine group, NH2, also known as an amino group. And on the other side, you have a carboxylic acid group, which is COOH, C with a double bonded O and an OH. So this molecule is an amine and an acid at the same time, hence the name amino acid. And then the R represents what's called the side chain of the amino acid, which is what distinguishes all 20 amino acids from one another. They all have different side chains, but other than the side chain, they all have pretty much the same structure. There's one called proline that has a little bit different structure than this, but the other 19 all have the same basic structure. We'll come back and talk a lot more about amino acids later in the course because proteins being some of the most important biological molecules, we're going to spend a fair amount of time talking about proteins and illustrating them. All right, last thing I want to talk about today are different kinds of carbon rings. Once the projector catches up with me. There we go. So we've talked about straight chains of carbons, just a bunch of carbons connected to one another in a straight chain with lots of hydrogens sticking off of them. Back in the mid-1800s, I mentioned the name Kekule before. I said that those little stick figure drawings of molecules are called Kekule diagrams. They're named after a very important chemist from the 1850s and 1860s. I just love his name because it's one of these really pompous sounding European names. He was actually Austrian royalty. He was a baron. So his full name was Baron Friedrich August Kekule von Stradonitz. And very, very important figure in the history of chemistry. He came up with a lot of interesting things. And one of the things that he's credited with, besides creating those Kekule diagrams, is the discovery of carbon rings. And they knew at that time about chains of carbon atoms, and they knew about alkanes and so forth. They knew you could have chains of carbons connected with single bonds. They knew you could have chains of carbons connected with double bonds and so forth. But there was one group of carbon chains that he couldn't quite explain because it seemed to have fewer hydrogens than it was supposed to. And the story goes that he had a dream one night about a snake chasing its own tail. So I've drawn this creature, which is clearly not a snake because snakes don't have pointy ears. They don't have external ears at all, but I don't know why I drew this thing to look like it has little pointy ears, but whatever. He imagined the snake reaching around and biting itself in the tail, and he realized that if a straight chain of carbon atoms were to wrap around and connect to itself at the other end, that would account for the two missing hydrogens at the ends of the carbon chain. And so he discovered these what are called cyclic alkanes, or chains of carbons that wrap around and bite themselves in the tail to create a complete ring. Now, if you think about it, there's no such thing as cyclomethane because methane is one carbon. It doesn't have a tail to wrap around and bite. You can't really have cycloethane either. If you have a 2-carbon chain, again, it can't really wrap around and the carbons connect to one another on opposite ends. I mean, You could have a double bond between the two carbons, but you can't have two carbons forming a ring. Theoretically, you could have a 3-carbon ring that would be called cyclopropane. You just add the word cyclo at the beginning to indicate that it's a ring. But cyclopropane is extremely rare, certainly rare in nature. You can force it to happen in a lab, but then it spontaneously breaks apart. The reason that cyclopropane is really rare is because if you look at the angle between those carbon bonds, it's an angle of 60 degrees. Remember that carbon normally forms a tetrahedral arrangement with angles of 109.5 degrees. That means that in order to force the bonds down to 60 degrees, the bonds are under a tremendous amount of strain, and they will just spontaneously rip themselves apart, and cyclopropane will just instantly convert into regular straight propane. Same thing is true of cyclobutane, although it's not quite as rare. I think you still have to generally make it in a lab. 4-carbon ring, the bond angles are 90 degrees, which is still less than 109.5. So these bonds would be under strain, and this thing would most likely rip itself open to become just regular butane. But what's much more common are cyclopentane and cyclohexane, a 5-carbon ring or a 6-carbon ring. If you look at the bond angles that form in a 5-carbon ring and a 6-carbon ring, they're pretty darn close to 109.5. They're only a degree or two off. And turns out that in reality, the bond angles are even closer to 109.5 degrees, because if you look at these things in 3 dimension, they don't simply lie in a flat plane like this. There's actually a little bit of bending and distortion of the ring that brings those angles a little closer to the desired 109.5 degree angle. So in cyclopentane, we've got 5-carbon rings with 2 hydrogens on each carbon to fill up, the valence of each carbon atom. And if you were to look at this thing kind of from the side, if you were to rotate it around in 3D, you'd see that those 5 carbons are not lying in the same plane, that one of the carbons is kind of tilted upwards to give it a little bit of a pucker. So it's not completely flat. Cyclohexane, similar thing. The angles between the carbons in cyclohexane are a little bit bigger than 109.5 degrees, but by distorting this thing in 3 dimensions, the bond angles end up a little closer to that desired goal of 109.5. And cyclohexane can take on 2 different configurations. There's what's known as the chair configuration or the boat configuration. And I don't know how well you can tell what's going on from these drawings, but in a chair configuration, imagine that the white part in the middle are 4 carbon atoms that are all lying in the same flat plane, kind of like the seat of a chair. Then there's 1 carbon atom at this corner point, which is raised up relative to the seat. It's like the back of the chair. And then there's another carbon that is tilted downward towards the floor. That's like if you're sitting in a chair with a footrest, like a lounge chair outside by the pool. You got the seat, you got the back, and you got the footrest of the chair. So one side tilts up, one side tilts down to create this chair configuration. And I'll show you a 3D model of this in a few minutes so you can see what that looks like. The other configure is like a boat. I'd call it a canoe. If you've ever seen a canoe, canoes have, forgetting the name of the word, but there's a term for the fact that canoes tend to tilt up in the front and up in the back. So in the boat configuration, you have 1 carbon that's raised up above the flat plane on one side, and the other carbon on the other side is also raised up above the flat plane. So if you kind of looked at this from sideways, from the side, you'd see a flat part in the middle and then tilted up at one end and tilted up at the other end as well, like the 2 ends of a canoe. All right, so these are all cyclic alkanes, so rings of carbons connected with single bonds. There are also cyclic alkenes, where you have double bonds between the carbons. Now, you could have a cyclic alkene that has just 1 double bond in it, but a very common molecule in biological molecules, a very common component of biological molecules is what's called cyclohexatriene. So it's cyclo, so that tells us it's a ring. Hexa tells us it's 6 carbons, and triene tells us that there are 3 double bonds in that ring. So here's what cyclohexatriene looks like down here. We've got 6 carbons, and there are a total of 3 double bonds in there. Now, you could draw it like that with the double bonds on the left, the upper right, and the bottom right, or you could draw it just like this, like you see over here on the right, where the double bonds are now in the upper left, bottom left, and on the right-hand side. And for a long time, in chemistry, they would teach you that the double bonds actually oscillated back and forth. Like for 1 nanosecond, it would look like this on the left, and then the next nanosecond, it would jump to the configuration on the right, and then it would bounce back to the left and then back to the right, that these things would just keep cycling back and forth between the 2 configurations, you know, like many, many times every millisecond. It turns out that's not exactly true. Now, I told you I wasn't going to get into, you know, orbitals and hybridization of orbitals and all that stuff, and I'm still not going to really get into that in any detail, but it turns out that because of the hybridization of the electron orbitals around the 6 carbons, the 6 carbons are actually sharing their electrons equally. All 6 carbons are equally sharing all of the bonding pairs of electrons that hold the ring together. And because of the fact that the 6 carbons are sharing those double bonds equally, or sharing those electrons equally, there are some symbols that are commonly used to represent this molecule. The hexagon with a circle or hexagon with a dashed circle in it indicates cyclohexatriene, which is more commonly called benzene. So here's benzene. A couple of things about benzene. For one thing, because there are all these double bonds being shared by the 6 carbons, that means that a lot of the valence of the carbons is taken up by the bonding between the carbons. Each carbon only has a single hydrogen attached to it, whereas earlier when we looked at cyclohexane, because there were only single bonds between the carbons, each carbon had 2 hydrogens on it. In benzene, each carbon only has 1 hydrogen on it. And the geometry of those bonds is that because of the double bonds in here, all these bonds are very close to looking like a planar molecule, where all the bonds have equal angles of 120 degrees. And in benzene, there's no pucker. There's no boat or chair. The boat or chair are only found in cyclohexane with single bonds. In benzene, with these double bonds, the entire molecule is completely flat. All of these atoms lie in the same flat plane. So benzene itself is a toxic chemical. You really don't want to be around benzene by itself. But interestingly, the benzene ring is a very important side chain in a lot of biological molecules. There's something called a phenyl group, which would be a benzene ring that's attached to some larger molecule as a side chain. There's something called phenol, which is benzene with an OH or alcohol group added to it. And that phenol can also be a side chain off of something else. There are a couple of amino acids that have these benzene rings in their side chains. There's something called phenylalanine, which has a phenyl group attached to it. There's a molecule called tryptophan that I believe it's a benzene ring, or it's definitely a ring in the side chain of tryptophan. So even some of the amino acids have these rings in their side chains. You could turn benzene into a carboxylic acid. You can add an acid group to it, a carboxylic acid, the COOH, to make benzoic acid. Just kind of an interesting molecule. If you add a methyl group to benzene, it's called toluene. And if you then add 3 nitrate groups to that, NO2s, you have trinitrotoluene, or TNT, which is a very powerful explosive. So I don't know about all of you. You may find this stuff boring, but I'm always fascinated by how chemical structures, influence the chemical behavior of all of these molecules. I mean, you've got benzene, which is a toxic, I believe it's carcinogenic, nasty chemical. You stick a methyl group on there and some nitrite groups to make trinitotoluene. You got a super powerful explosive. So, and things like esters, that make all of these flavors and smells. Just interesting how these chemical compounds are responsible for all of these things that you encounter in day-to-day life. I mean, you don't exactly counter TNT in day-to-day life, but it's an important thing that's used in industry anyway. So let me just, before we wrap up, let me share some of these models with you of these different kinds of molecules. So going back to the beginning of the lecture, this is a simple 3-carbon chain with all of the carbons connected by single bonds. It's fully saturated and has every possible hydrogen that it could have. This is propane. So prop is the prefix for 3. And since they're all bonded by single bonds, we use the suffix ane, or the ending ane. So that's propane. And very similar to that, this is octane. It's an 8-carbon chain, all connected with single bonds. And you notice that zigzag that I was talking about, where all of the carbons are connected to one another by 109.5-degree angles. So if you look at it kind of in the big picture, it looks straight, but if you zoom in on it, you realize it's zigzagging back and forth. And let's see. So here's one that's branching. So this has side chains on it. So if you rotate this around in space, we have to figure out, all right, what's the longest continuous chain of carbons in here? Well, I could start over here at the far left. That would be number 1, number 2, number 3, number 4, number 5. So that would be pentane. But I could just as easily start up here at the top and start counting there. 1, 2, 3, 4, 5. Or I could start down here. 1, 2, 3, 4, 5. So there are basically 3 identical carbons over here on the far left. It doesn't matter which one I start counting from. I'm always going to end up with a 5-carbon chain. I'm always going to end up with pentane. Now I could start counting from the far right. Maybe I could rotate it around like this and say, oh, let me start here at the far left, 1, 2, 3, 4, 5. But I wouldn't do that because I know there must be some side branches over here, and they're closer to this end, to the far right than they are to the far left. So in this, orienting it this way, I'd have to start counting with my number 1 carbon over here on the right. It could be any of these 3, but it would be one of these carbons on the right that I'd start with. So my main chain has 5 carbons in it. That means that there's a methyl group attached to the number 2 carbon. There's another methyl group attached to the number 2 carbon. So this is called 2,2-dimethyl pentane. Pentane, 5-carbon chain with 2 methyl groups, both of them attached in the number 2 position. So 2,2-dimethyl pentane. Here's an alkene, meaning there's a double bond between 2 of the carbons. The only problem is, one thing I don't like about Chimera. I love this program. I use it all the time, but it has one drawback, and that's the fact that it doesn't show the double bonds. So how do I know there's a double bond in here? Let me ask you, how do I know there's a double bond in there? Because of the single hydrogen atoms at two of those carbon positions. These two carbons, I don't know if you can see the ones I'm circling with the cursor, but those two carbons only have a single hydrogen on each one. You know, I zoom in on them so you can see them. These two these two carbons only have one hydrogen on them, whereas all the others have two carbons on each one, or three at the very ends. So it's unsaturated right here. It's missing a couple hydrogens. So I know that means there's a double bond between those two carbons. So how many carbons do we have here? We got 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 carbons. So that means the name begins with non, N-O-N. And it's got one double bond in it. That means it's an alkene. So this is nonene, N-O-N-E-N-E. And specifically, this would be 3 nonene because that double bond would lie right after the third carbon in the chain. I'd start counting from the left because that's closer to where that double bond is. I wouldn't start counting at the right because then it would be farther away. And here is looks like, boy, why is that bond so long? Well, when you view it as a ball and stick, you realize actually there's atoms there. And I can tell that these two carbons are triple bonded to one another because they don't have any hydrogens on them. There are 3 bonds connecting those two carbons together, and then a single bond connecting those two carbons to neighboring carbons. So there are no valence left over for any hydrogens on here. So this is called hexyne with a Hexyne. It's a 6 carbon chain with a triple bond in it. So it's an example of an alkyne. Let's see. Got some cyclics here. Here is cyclopentane. So when I look at it this way, it looks like a nice perfect pentagon, 5 carbon ring with 2 hydrogens on each carbon. That tells me that these are all single bonds. But if I look at this from the side, if I can line up those 4 of those carbon atoms, so they're all lying basically in the same flat plane, you notice there's one carbon, the one on the far left, that's tilted up relative to the other 4. So that's the pucker that we see in cyclopentane in a 5 carbon ring. And then with cyclohexane, this is our 6 carbon chain with all single bonds. If I orient this, so you look at it this way and it just looks like a hexagon. But if I can look at it from the side and get 4 of these lying in the same plane, notice there's one carbon on the far left that's tilted up relative to these other 4 in the middle. And then another carbon over here on the right that's tilted down relative to the other 4 in the middle. This is called the chair configuration of cyclohexane. It's like a lounge chair. We've got the seat in the middle made up of 4 carbons. You've got the backrest raised up above the seat, and then you got the footrest tilted down below the seat. By the way, this is not just found in cyclohexane. There are a lot of things that have a 6-sided ring shape, like glucose. Now, glucose is not 6 carbons, it's 5 carbons plus an oxygen, but it still forms a 6-sided ring like this. And glucose also exists as both a chair and a boat configuration. So that was the chair. Here's the boat. Get the bonds of the atoms on there. So once you look at it this way and it looks like just a plain old hexagon. But you look at it from the side, we try to line up 4 of those atoms so they lie in the same flat plane. Then we've got one carbon that's tilted up on one side and another carbon that's also tilted up on the other side. That's like the bow and the stern of our canoe or our boat. So that's the boat configuration of cyclohexane. And then here's benzene. And once again, Chimera doesn't show the double bonds, although there is a tool. Maybe it's over here. Oh, yeah, it's over here. Rings. There we go. There's a tool in Chimera that lets you turn on the little circle. And is it showing up there on screen? Anybody see the circle? Oh, there it is. It's just barely visible. It's really faint for some reason. That's the little circle symbol that you put in the middle of a benzene ring to indicate the double bonds that are being shared equally by all 6 carbons. But the other way you can tell that these carbons are joined by double bonds is the fact that we've only got the single hydrogen on each carbon. And if we look at this benzene molecule from the side, you'll see that it's completely flat. And all these bond angles are 120-degree angles. And here's TNT, trinitrotoluene. So that's our benzene ring in the middle. And I don't know if it shows up, it's barely showing up there. A little circle in the middle, but so we've got benzene, we've got a methyl group up at the top, CH3, and then we've got 3 nitrite groups to make trinitrotoluene or TNT. Here's an alcohol. This is ethyl alcohol or ethanol. So it's just ethane, but with the addition of an OH group. Looks like one of those little balloon animals that clowns make. It's our OH. By the way, notice the OH that the bonds on that oxygen have that bent configuration. That's an alcohol. Here is our carboxylic acid. This is ethanoic acid or acetic acid, vinegar. 2-carbon chain, so that's ethane. But we've got a double bonded oxygen down here and an OH group up there, so it's COOH. So that's a carboxylic acid. Here's another one. This is a long carbon chain, but it's still got that carboxylic acid down at one end. If we zoom in on this end, we've got a double bonded oxygen and an OH. This is a molecule called arachidonic acid that we'll come back and talk about later. It's kind of an important molecule. Here's an aldehyde, double bonded oxygen at the end of the carbon chain. Contrast that with a ketone, where the double bonded oxygen is not at the end of the chain, but it's somewhere in the middle of the chain. Here's an ether. So we've got a methyl group on one side and an ethyl group on the other side. They've been joined by this oxygen. So this would be, it says on my, if you look on my desktop, if you look at the name of the file, it says methyl ethyl ether, but I believe it's actually more correctly called ethyl methyl ether because you name the alkyl groups in alphabetical order. So ethyl methyl ether. And I forget what smell this is, but this is probably, oh no, I'm sorry. Those are esters, never mind. This may be the kind of ether that was used popularly in anesthesia. Okay, here's the smell of apples. This is an ester. So not ethers, but esters are the smells. So it's the actual smell of the real thing. But when they make artificial whatever, all they're doing is just manufacturing this stuff in a lab. So there's a chemical called vanillin, which is the thing that gives vanilla its smell. You can extract that from vanilla beans, or much cheaper, you can make it in the lab. But it's the same thing.
Is there a reason why they kind of like taste different though? Like it's
Yes.
apple flavored, but
Yeah, no, these are great questions. So in case you can't hear, Joelle's asking about the, what's the difference between the naturally occurring flavor and the artificial stuff? And the difference is there's not really a difference, sort of. The active ingredient that gives things the smell of strawberries or the smell of vanilla or whatever, it doesn't matter if you extract it from the natural plant or make it in a lab. That's why, I get a kick out of people who are worried about, oh, artificial flavor. Well, it's the same damn thing you're getting from the vanilla bean. It's just made in a lab, but it's the same chemical. The difference though, why do like things made out of real vanilla taste different when the ones made out of artificial vanilla? It's the other stuff that's in the vanilla bean or the apple or the strawberry or whatever. So even though we immediately recognize the smell of vanilla or the smell of apple or strawberry from the chemical made in the lab, it may not be completely reproducing the flavor because of all the other chemicals that are present in there. By the way, another little tangent. Anybody in here like wine? A few people are sheepishly raising their hand. Sure, yeah, why not? I used to get a kick out of these wine aficionados who would, they'd hold up a glass of red wine under their nose and they'd swirl it around and it's like, oh, I detect notes of cherry and chocolate and persimmons and all this stuff. It's like, you people are full of it. But then I realized that it's really true. Because what happens when you make wine is you take a grape, which is basically a big bag of sugar, and you crush it up and you give it to yeast and they eat the sugar and they turn it into alcohol. And carbon dioxide too. And if you want champagne, you keep the carbon dioxide. But most of the time with wine, you let the carbon dioxide fall off, but the yeast convert the sugar in the grapes to alcohol. But there's more to a grape than just a bag of sugar water. Grapes are living things. They're living tissue from a plant. So that means they have cells, which have proteins, and they have nucleic acids, and they have all kinds of other stuff in the cells that make up that grape. And the yeast, not only do they eat the sugar and turn the sugar into alcohol, but they also eat the protein and the nucleic acids and all the other stuff. And a lot of that stuff gets converted into esters, which actually are the smell or taste of chocolate or strawberries or persimmons or whatever it is that people smell or taste when they drink wine. So it's just that people who have really trained to carefully taste wines, they have trained themselves to detect very tiny amounts of these different esters that are present. So the flavors really are there. It's just whether you take the time to really
learn how to detect those flavors. So they're not quite as pompous as they sound.
They're still pompous, but they've got a good reason why they taste those things. And here's an amine. So something that has NH2 added to it. One other thing to notice here. Notice that the nitrogen has 3 bonds that have that pyramid geometry. The 3 bonds look a little bit like the legs of a tripod. The legs are spread out pretty wide, but still like 3 legs sticking down from under that nitrogen. And then an amide is very similar. And for some reason, this particular molecule, the 3 bonds on that nitrogen are not behaving the way they're supposed to. They should look like a pyramid. They shouldn't look like they're all flat like this. But anyway, you got your NH2 plus you've got your double bonded oxygen on the carbon. So that makes this an amide. So that is what I wanted to show you today. Just a reminder, in case anybody came in late or joined the Zoom late, we do have a quiz on Wednesday, which will cover these last 2 lectures. So last Wednesday's general chemistry lecture, as well as today's organic chemistry lecture. So